And hello everyone, this is another nuclear power plant simulator, and this one is developed by the University of Manchester Dalton Nuclear Institute. Similarly to the previous one that I published, this is the kind of simulators that I will call the three knob simulator. You can already see in the lower part, like there is a reactor, coolant, and generator knob. It can vary a bit between versions, but at the end you always have a control in each one of the stages of the nuclear power plant, and it's quite simple. You need to adjust them so none of the parts of the nuclear power plant surpasses the maximum temperature or the maximum power or the maximum whatever. This simulator is quite nice in the sense that it has a very impressive 3D graphics, and actually these graphics change depending on the state of the nuclear power plant. So this is quite nice, I would say, for someone who is learning about nuclear power plants. I will read like the instructions, so they are quite short, so it will be very fast, and then I will start the nuclear power plant. So here we have an explanation of the different elements. We could directly click in each of them in the diagram to go directly to the explanation of each of them, but I will follow this tutorial by clicking next. So first we have the fuel reactor core. Nuclear fission occurs when a neutron makes an impact with a uranium-235, which is an isotope of the uranium element, causing it to become unstable and split into two small atoms and release a large amount of heat. The fuel in a pressurized water reactor is in the form of thousands of cylindrical uranium dioxide pellets, around 5% of uranium-235, which is the enrichment, loaded into zirconium tubes and assembled into the core. Here we have an image of the core, in which we have two deflectors in the two sides of the core where we have the fuel elements, and the water is inserted from the bottom and goes upwards and comes out from the core from this outlet. And all this is in liquid state because this is a pressure vessel. A pressure water reactor, so there is no boiling here. And here we have the image where we see actually the fuel elements, which are these rectangular prisms with these pipes here that are the absorber rods. Control rods or absorber rods. Control rods govern the nuclear reaction by absorbing excess neutrons produced by the fission process. The farther these are inserted into the reactor core, the less heat is produced by the reactor. Okay, the overall concept is right, but I would say you don't really control the heat that the reactor produces by controlling the control rods. Ultimately, yes, but directly what you control is the reactivity. And the reactivity will change the neutron flux, but you need to know the history of previous activity to know the actual state. So it's not like directly you put a position of control rod and you obtain a thermal output. It depends on the previous history of the reactor and many other parameters. And here you see 0%, which indicates that the control rods are totally inserted at the moment. And we will go to the next. Pressure vessel. The pressure vessel is a large steel... Wait, why it changed like that? Pressure vessel is a large steel cylinder that houses the reactor core. The coolant flows into the bottom of the pressure vessel via the inlet pipe, and is heated by the core before leaving the top via the outlet pipe. Okay, I already introduced this before, but the reason why we introduce the water in the bottom is because the water volume change because of the heat will actually help by convection this movement. So in case there is a failure of the cooling pumps, the reactor has some residual cooling just because of the heating of the water that makes it circulate a bit. That's why this direction. And also because in the event of boiling, which is an accident because this is not intended to work with a boiling water, but in case of some boiling starts to happen in some part of the reactor, the boiling will, because of gravity, will push upwards to go to the upper part. So if it was the contrary, if the water entered from the top and went to the bottom and it starts boiling, the boiling will reduce the velocity of the water around the boiling point, making it more likely for other parts of the reactor to start boiling. So that's one reason why you want this bottom to top flags. Next, coolant pump. Water is used to transport the heat from the reactor core through the primary circuit to the steam generators. The water also moderates... why the image appears so slowly? Maybe my internet is not fast. The water also moderates or slows down the neutrons producing the fission process, which is important for the reaction as it allows the neutrons to collide more effectively with the uranium-235 atoms. Primary circuit pumps. 4 large pumps are used to circulate the coolant around the primary loop. The pumps are also used to heat the coolant during the startup of the reactor. So this is interesting. Actually, neutrons not only collide with U-235, they also collide with other isotopes and make them become fissile, like uranium-238, I think, which is a fertile isotope of uranium. When it captures one extra neutron, it becomes plutonium-239, or 238. This is the atomic number, not the weight. So, yeah, that's right. And this is a water-cooled, water-moderated reactor. So the water has 2 functions. One is cooling, so extracting heat from the reactor. The other is moderate, which is remove energy from neutrons. So there is a higher probability of impact with a core. There is some nuclear physics or neutronics that explain why at lower energies you have higher chance of hitting a core. It's not obvious because if you just look at geometry, like the probability of you being hit by a bullet, of someone randomly shooting bullets, it doesn't depend on the velocity of the bullets. But in neutronics, it's like that. So lower energy, which can also be called as lower energy neutrons, which can also be called thermal neutrons, have higher probability of impacting another core, around 1,000 times more probability. And the cooling pumps, which actually also heat the water in the case of a startup. Next, we go to the pressurizer. The pressurizer is responsible for maintaining the high pressure of the water coolant, which allows it to be heated to 320 degrees Celsius, and the image appearing at the right moment. So there is a pressurizer which is a volume attached to the primary circuit, and actually it has a shower inside, which operators can control, like opening or closing a valve. You can imagine that the pressurizer is full of water until maybe 1/3 here. So here you have water, in the upper part you have air or nitrogen or water steam, because this water is hot. And what do you do if you want to reduce, because of some reason, pressure in the reactor very quickly? You open the shower in the top, and because you are making cold water rain in hot steam or hot gas, well, yes, hot steam in this case, the hot steam will condensate very quickly by reducing a lot its volume, and this will automatically reduce the pressure in the primary circuit. Steam generators. The steam generators transfer the energy from the very hot coolant in the primary circuit to the secondary circuit, turning water into steam, which is used to drive the turbines. Yes, so basically this is very different from an RBMK nuclear power plant, because here we don't let the water that touches the nuclear fuel go through the turbine. So in some sense it is more safe, because it allows you to have a more compact primary circuit, which does not include turbines, and this allows to build a strong containment, which can contain 0.5 bar of pressure in case of loss of primary coolant accident, quite more economically than in the case of a boiling water reactor, for instance. Actually, in a boiling water reactor, the containment doesn't contain all the contaminated water by fuel, because the turbines need to be placed outside the containment. It would be too expensive to place the steam turbines inside the containment in a boiling water reactor, or in an RBMK. So this is one advantage. We have a primary circuit, then we have a heat exchanger, and then the heat that boils water in the secondary circuit is the one that will generate the mechanical power in a turbine outside the containment. Of course, this reduces thermal efficiency because here you have a non-ideal system in which you need to transfer heat from one circuit to the other, so you lose thermal efficiency here. And next, finally, we end up in the turbine with the high pressure part. I will not read, I'm tired of reading. You will the inlet of the main steam line will go to the high pressure part of the turbine, and to increase efficiency, the turbine has several parts, has the high pressure and the low pressure. So these are in series. Once the steam comes out from the high pressure turbine with reduced pressure because it gave part of its potential energy to make the turbine spin, then it goes through the low pressure turbine, which is a much bigger in size because the steam already decompressed, it lost pressure, so it occupies much more volume. That's why the low pressure is much bigger. And then you see that the shaft of the turbine is connected to a generator, which will generate the AC current that then it's injected into the grid. Next. Yeah, this is the generator, I just commented about it. And the famous condenser. The condenser is the part where the steam that comes out from the turbine is turned into water by cooling it. So to cool it, we use some outside water, outside from the plant. It could be from a lake, from a river, from the sea. Here it's level like sea. So here we have a high surface area of plumbing, in which we pump cold water, and the steam, when touches this water, it condenses. It's not explained here, but actually the fact of condensating hot steam makes it shrink. So here we have vacuum. Operators of RBMK simulator, the legacy continuous, will know about this vacuum. And this vacuum actually is the one that runs the turbine because it's in the outlet part of the low pressure turbine. So it's actually what runs it. And then I think we made all the cycle. How to play? 1. The first step is to switch on the primary coolant pump heaters to heat the coolant to 290 degrees. 2. Next, you start the reaction process by lifting the control rod slightly less than 10%, then try to increase power output to 1040 megawatts using the steam demand and control rod controllers together. So steam demand here, control rod controllers here. And why not the coolant pumps? Okay. And 3. During day 1, try to follow the UK power demand and increase the power output to 1600 megawatts for the day, whilst keeping the coolant temperature within program range, which is the green part in this indicator. Then reduce it back to 1040 megawatts for the next night. This process is repeated for day 2. Okay. Until here, the explanation of the nuclear power plant and what are the rules of this game. So let's start. Click next.
Nuclear reactor simulator. Try and match the demand.
Okay, we see here demand 1040 megawatts. So now I will start the coolant pumps by switching them on here with this knob. And we see how the temperature increases. We are already in green zone, so I will start pulling rods a bit. And you see that now the coolant temperature is too high, so I will start the steam demand. So you see, as I increase steam demand, coolant temperature decreases. So it's time to pull a bit more rods, always trying to keep the coolant temperature in the green zone, and then increase steam demand. Again, increase reactor activity. And now we see that the 3 indicators are in the green area. We're generating a power output of 1079 megawatts, a bit above of the needed.
Demand matched. Well done.
Thank you. And I will decrease a bit just to match it more exactly. So if you try to operate the steam demand, the effect is quite brutal. So it's very sensitive, this slider here. But if you leave these two alone and you reduce a bit reactor activity, you see I'm reducing a lot reactor activity and it's barely reducing the
Demand
output.
matched.
So
Well done.
for fine adjustments, it's better to use reactor, but always trying to keep the coolant pump in the temperature range. So I will increase a bit here. I mean decrease steam demand, and now I'm almost matching the demand. Please move steam demand up while keeping coolant hot. Yeah. And if you want even more finer, you see now I have I'm matching exactly the demand at 1 megawatt precision. Okay, so we are at 8 in the day 1. So probably now the demand will start to rise. What did the instruction say? Like during the day 1, increase the demand, increase the output to 1,600 megawatts. But now it's going to be the night, right? After 10 p.m. Who knows? Because it's UK. Maybe they have the time upside down. And you see here the animation how it has like, if you have ever visited a nuclear power plant, they always have a 3D model with these lights like in a Christmas tree. And it's like this doesn't really emulate a nuclear power plant, but the model that people see in the demonstration area of nuclear power plants. And actually you can click things now, like steam generator, and you will see like the explanation that we already see before. And actually there is much more data here, like the material, dimensions, tube diameters, etc. Design pressure is 17.5 megapascal. Okay, demand has increased. So let's increase a bit reactor activity until the coolant is at the maximum, and now increase steam demand. And you see demand is increasing progressively, so we need to keep doing fine adjustments. Now it's at 1300 megawatts. Okay, a bit more. And the coolant temperature is quite low now, so let's increase reactor activity a bit. Okay, I'm quite matching the output, so it's the demand, so it's quite good. I don't find this very realistic because in reality...
Demand matched. Well done.
Thanks. In reality, you don't really change output of nuclear power plants. They are always at their nominal because it's quite difficult actually to change the reactor regime. And if you do, you create transients. So you create poisons, and then these poisons, because they are delayed with the actual activity, it's very difficult to balance them out. So nuclear power plants are always at nominal or 100% power. And in the bidding of energy for the electric grid, there is an order. Like the first to bid, I think it's and demand is going down. The first to bid is like the fossil fuels. And then you have renewable. And when already all the energy is on the market, then the nuclear sells their energy or something like that. So I mean, nuclear power plants don't really try to match demand. It's this is a duty of the other kind of technologies in the grid. But this game is quite fine, I think. Okay, reduce a bit reactor activity. And I was reading this here. Yeah, this is a typical pressure for a pressure water reactor.
Demand matched.
Like
well done.
The working pressure will be around 15 megapascal, so the design of the steam generator is a bit above it. And you see this is the typical Westinghouse design in which you have vertical steam separators. steam generators. For instance, in the Russian VVERs, sorry, I said 3 V's, 2 V's, VVER or WWER in Western languages, these separators are placed horizontally, and the demand is increasing. Let's increase generator output. Let's increase core activity. So by placing these steam generators horizontally, the VVERs can build a much smaller containment, which is more economical. But I guess it has some drawbacks because you need to design this differently. I mean, being vertical, it's optimal because, okay, the game is finished. You got 269 points. Your performance is 3 stars. Nice. So I don't really know what the points mean. I played this before and I got 800 points. And before I was not talking, so I was really concentrating to match the demand, the maximum possible. So I guess maybe the maximum points you can get is 1000, but I'm just guessing. I just got around 800 before. So that's a nice game, and I like all the informations that are given here. The only thing is that actually while playing you don't have much time to read them. And now when you finish, like you don't have the opportunity to read them anymore. So as I was saying, I think this is the typical design of Westinghouse AP1000 or so, which are 4 steam generators placed vertically inside the containment, which quite limits or constrains you in the design of the containing building. And VVERs, Russian VVERs, which are always pressure water reactors with very similar specs to this one. I mean, in terms of primary pressure, secondary pressure, power output, around 1000 megawatts, etc. They have, I think it's 3, not 4, but I'm not really sure about that. 3 steam generators placed horizontally inside the building, which is quite interesting. And the foil assemblies, they are not quadrangular prismas, they are like hexagonal, which I guess it gives a better controllability of the local activity of the reactor. Okay, I hope you enjoy this video. I think this is quite a nice educative simulator by the University of Manchester. See you in the next video. Bye.